simple harmonic motion and oscillations. We're going to have a look at different sorts of pendula and what they do. So let's go and have a look at this pendulum and see something about it. Right, if we stop this pendulum. Now, the pendulum is simply here a weight, and this weight is held up by a string from a pivot point. And what we can do with this is we can make certain observations. So the first of these observations is that if I let go, then the pendulum won't come back to the same position. It's gradually going to lose energy, but it's going to lose energy very slowly over time. The next observation we can make is about the timing of this pendulum. Let's do some simple timing, and I'm going to measure where it's going to get to my finger. So we go 1, 2, 3, 4, 5, 6, 7, and it's taking about the same amount of time to go from this point over to there and back again. And that was just me doing a simple counting experiment, but what we could do is we could do this more accurately. So I could put a point here, I can get a stopwatch, and what we could do is measure how we're doing with this. And with a simple stopwatch, all I need to do is measure the time it's going to do to, say, 10 oscillations. So I can measure 10 oscillations, and we can measure the time to do this, and then we can divide by 10, and that's going to give me the time it takes to go from one side to the other and back again. We call that its period. Now what I've done is, in fact, I've got a slightly more elegant setup here, and if we zoom up to the top, what I've got is a little sensor up here. If I can, wrong way, zoom in on this sensor, we can see that I've got a piece of string tied here to this rotation sensor, and this is moving here left to right, and I'm going to change that round here so you can see that a little bit more clearly, and we can see that it's changing as, in fact, the pendulum is moving down here. Well, let's go over and see if we can actually record this. Now what I've done is I've got this set up, so if I now go to 3, we've got here my screen set up, and what I'm going to do is I've got my hardware. My hardware is our rotation sensor, and what I'm going to do is I'm going to record this about 20 times per second, and let's just see what's happening. Well, doesn't appear to be a lot, does it? But let's look at this a little bit more zoomed in, and there we can see we've got this motion forwards and backwards with time, so it makes a sinusoidal wave. Let's record this, and we can see that as this moves, we're getting the waves moving along. So I'm measuring here simply the position, and we can measure here the time it takes. So we can spread this out if I want to, and here if I take this point here at 1.5 seconds, it's at the bottom, and to complete this here we're at this point here, which is about 3.25. It's an approximate measure here. So I can measure that we've taken 1.75 seconds to go from one place to the other side and return back again. And we can see that this repeats, and it takes the same time to do it for the next oscillation and the same time for the next oscillation. Now let's have a look at doing this same experiment, but what I'm going to do is I'm going to change the mass. So doing this, it took from 1.5 to 3.25, so 1.75 seconds, and that is with on here 100 gram mass. Let's suppose we stop this and I take off 50 grams. So now I've got a 50 gram mass that's swinging. It's not swinging centre of the pole, it's swinging roughly centre of the edge of this retort stand. If we now go and record this, and if we look, we can measure the time from here, which is just over 2 here, and the mass doesn't seem to be making a great difference here to the pendulum. In fact, we find that the mass doesn't really affect the pendulum. I say really because if they make the mass too light, then the pendulum doesn't work properly. But the mass isn't changing the period. Alright, so just looking at a couple of simple bits and pieces, we can see this pendulum moving. Now, I'm going to go back to making my pendulum about 100 grams, and changing the mass of the pendulum then really has no effect, but other things can have an effect on this pendulum. So one of the things that we can do is we could make this string shorter. And so if I make this string a little bit shorter, and I'm just going to simply tie a knot in it. I'm just going to do a very crude little experiment. I'm going to make this string shorter. So instead of reaching down to the bottom, Let's give this a little bit of movement. And let's go and have a look and see what's happening to this. So I'm going to start my software running. I'm going to record. And is there making any difference? Well, the easiest way is let's compare these two runs. There we are. And can we see that there's a change? Well, without doing anything fancy here, we can see that the length is different. This is the first one, and we've made it shorter, and I can't easily wind this software along. It doesn't work quite like that to superimpose the two waves over one another, but we can see here they were working together and they're getting out of phase because this one is shorter. So as we shorten the string, so the period gets quicker. So where do we start with some of these things and having a look at bits and pieces? Well, most of these things have been known about pendula for a long time, and if we go back and have a look at some clocks, we see that what we have is a system. Let's get the camera right. And if I take my pendulum and I swing my pendulum from one side to the other, then if I set this, that this distance, and it came back with this length, was 1 second, then this is going to be how I keep my time on my clock. Now, what happens if this pendulum moves a lot less distance? So that's our first investigation to have a look at. So what I want to do is see if we keep the length of the pendulum the same, but we change the distance it moves, is it going to affect the time taken? Is it going to affect the period? Let's have a look at this one. So I put a little knot in my pendulum. I'm just going to now, for convenience sake, undo this, which is why I only made a temporary change here. And what we're going to look at is a fairly little swing. So let's give this a little swing. And what we're going to do is measure the time taken to go from one side to the other. So let's clear this out and we'll start to record what we're doing. I didn't clear it out very well, did I? So there's my pendulum moving with its little swing, and the amplitude is not great here, so we're just giving it a little swing. Let's now do the same thing, but we're going to give it a much bigger swing. So I'm going to give this pendulum now a much bigger swing. this time let's start recording. And I think that is quite conclusive proof. Here they're matching up beautifully, more by luck than judgment I might add, but you can see the time taken for a long swing and a small swing is exactly the same. So what we can see from here is very simply that changing the amplitude of the swing doesn't change the time period, and this is what they found with clocks. They found that it didn't matter whether it was a large swing or whether it was a small swing. The time taken was the same as long as the mass stayed the same, and the mass has very little effect on this, and most importantly the length of the pendulum stays the same. So as long as that does, then we have here something that will accurately keep time. So with this knowledge, basically managed to produce all sorts of information. So here we're going to start with simple harmonic motion. For anyone who thinks this is difficult, then all you have to do is look at difficult harmonic motion, and we can find that this really is quite easy. So basically we found out that although basically here we could say the oscillation dies away, the time period is constant. And this is our first inkling. This in fact was noticed by Galileo way back in 1581. He watched some lamps in the Pisa cathedral swinging backwards and forwards, and he realized that this could be used for timekeeping. Even if you've now got one of these little watches, this still relies on oscillation to try and keep it going. This is a quartz watch, and this quartz watch uses the oscillations in a piece of quartz, the vibration in a quartz crystal, the natural vibration of atoms, to record the same time period. Now this works largely when we've got one of these things that works at the same time. If I take this and give it a whacking great big swing, then this doesn't work. It only works if we use relatively small movements. And as long as we use small movements, this seems to work brilliantly. So we've got this idea that we can change the time taken by lengthening and shortening the string, and we can simply not worry about the mass on here, because the mass on here doesn't make any difference really with the oscillation. So as long as we keep small angles, we keep the weights reasonable, then we don't have any problem with this simple harmonic motion. That's with the pendulum. Now I've got another pendulum I want to set up and have a look at. So let's see if we can do this one, and what we're going to do is set up a different type of pendulum. Now this different type of pendulum, I'm just going to unplug that one on, and what I'm going to use for this one is a different sort of sensor. I'm in fact going to use a ultrasonic sensor here. And this ultrasonic sensor is going to have a look at this item here. This is simply a weight with a piece of card. And here I go. What I'm going to do is up on my ceiling, I've got a force sensor, and I'm going to attach to that force sensor spring, and to that spring this piece of card. Underneath this I'm going to place my ultrasonic sensor, and let's get this set up. So I'm going to have that sensor linked, but I've also got up here a force sensor, and this force sensor I'm also going to record, so I can actually record the force on here as well as the distance. Let's set the software up. What I'm going to do is, let's look at my hardware. I've got a motion sensor, and we're going to connect a new one here. I've got a high resolution force sensor. Okay, so we're going to do a new experiment. And let's just set up here. The graph, that'll do. And I'm going to select my measurement. I've got here my motion sensor. I'm going to measure the position, but I've also got another one. I'll do that one in a minute. Let's do this one first off. So let's set this going. So what I've got here is this little spring. What I can do is I can set this going, and I'm going to set it so it's over the sensor here, and let's see what happens when we start recording. What we're seeing is exactly the same type of motion we had before. With this one we can make a difference if I change the mass. So if I change the mass here, and let's put on now a larger mass, now what we should see is something else. Let's try it. So we've got that one going, let's set this recording. We're getting the same type of waveform, but this time from a spring. I'm just going to stop this simply because at the moment I don't want to hit myself with the machine, and I'll move that out of the way. Now let's have a look and see what we've got. Let's bring in the previous wave, and what do we notice with these waves? Well, we're seeing that if that was up, that one's up, that one's not quite the same, and they aren't quite in phase, are they? So as I am increasing the mass, so this time I'm changing the period. So with a spring it's working differently than with a pendulum. So this type of spring pendulum is different. I connected a force sensor to this, so let's see what happens when I change the force sensor as well. So let's have a look at that. So what we've got is down here ultrasonic sensor measuring the distance, but up the top here I've got a force sensor, and that we can measure the force. So what I'm going to do is, on this software, I'm just going to do a new experiment. There we are. And I'm going to select again my motion sensor, doing that. But what I can do is I can add a new y-axis to this, and this time I'm going to put in the force, and let's have a look and see what happens when we get this going. So let's pull this down. I'm going to let it go for a couple of goes. Basically the idea of doing this is to try and get this to sort of settle down, and this has got a fair bit of wind resistance. Let's start recording. Self-preservation, just trying to stop me knocking myself out with it. Well, we've got a force and we have here a position. If I change the position, you can see this is the one with the position, and if I change the force here, I can increase the resolution of the force, and we can see that my force, not quite as accurate perhaps as the distance here. We can see this is going down with time, and that's not helped by the fact that on here I've got a massive air brake. This is pushing the air, so this is going to slow this down. I can do it without this on, but trying to get the readings is a bit more difficult, but we'll try it. What I've now got to do on this one is to get a much closer line up with this force sensor, and hopefully I've done that. Now let's run this experiment again. So to do this, what I've got to do is get this going. Looks like it's in the right place. I'm moving out the way so I don't interfere with the sensor. And then if I record this, this has got a much more even movement. And it does work, it just requires me to line the thing up a little bit more accurately. So what can we see with this? Well, we can see that the force is actually moving in unison with the distance. So when this is at the top of its movement, then the force is at its lowest. As it goes down, so the force is increasing, so when it's at the bottom of its oscillation, then the force is greatest. But I needn't just measure position here. What I could do is I could measure the velocity. And now we can see that the velocity is rather different to where we've got the force. I'm just going to try and bring that down a little bit so we can see what's going on. If we take my pendulum, and I think that camera might be about the best one, when it's up the top here, right at the top, it's not moving. When it's right down here at the bottom, it's not moving. We can see stopped at the top and the bottom, and its greatest velocity will be when it's in the middle. So as it goes, it starts off not moving, accelerates, gets faster and faster, the highest velocity, and then it slows down till it's stopped. So we expect to find that our velocity, try not to kill myself again, the velocity will be greatest when we're halfway, and that is what we're finding. If we look at our acceleration, this is now opposite to what we had with the force, and that makes sense because the item is going to accelerate the greatest when it's at the stationary point moving up or down. So when this is down here, it's going to accelerate at its highest amount, and then it's going to decelerate to its lowest amount. So our acceleration is greatest at the bottom and at the top. And this we find exactly the same with the other pendulum. The problem is with that pendulum, trying to measure the force is a little bit more difficult, which is why I've gone to this system to do this. So we've got here an idea of the force that's going on, we've got an idea of the acceleration, we've got an idea of the velocity, and we've got an idea of the position, the distance. The distance and force are the same. The velocity is out by 90 degrees, and our acceleration is out by 180 degrees. So let's see if we can get some ideas about this. So we've got our wave. Let's first think about our velocity. So if we swing this, we try to think about what's going to happen with our velocity, and this is going to be greatest when we're at the midpoint. Let's think about the acceleration, and the acceleration is going to be greatest at the extremes of the swing. We think about our extremes here and here, and then the middle point is our equilibrium position. Does the size of this acceleration change? Well, to do that, we're going to change the mass. So I've got recorded here my acceleration. Now I'm going to run this experiment again, but this time, instead of using what is 150 grams, let's put on 200 grams. So I've now got a 200 gram mass. We can try this with 200 and 100 and see what's going to happen. So let's set this up. I have my 200 gram mass now. I'll give it a bit of movement, and what we can then do is record this. Now let's stop the experiment, and I'm going to take off 100 grams. This is going to move the oscillation position of this. I can't do anything about that. But if we now record this one again, the abnormalities were me moving. And let's stop this. Let's have a look at our two graphs. So this is our second one with a couple of anomalies in there, and what I'm going to do is bring in the previous run. Now let's have a look at what we've got. So this is run 3 and run 4. We've got not very much in the way of colour difference, so let's make this easier, and I'm going to set one at green. So that's my force and my acceleration. I'm going to make that lime green, and now we can see that the other force is going to be slightly different because the mass was different, but we can see that with 200 grams here the period was much longer than with the 100 grams. So we're affecting that because the acceleration is changing. So the acceleration here is basically a little bit less because it's taking a longer time to do that. But we can see our acceleration here is less. Green is smaller than the purple. Okay, so we've got some idea. The size of the acceleration is basically always towards the equilibrium point. So if we think about it, the acceleration is going towards that equilibrium point. And the acceleration here is directly proportional to the distance from the equilibrium position. So that's given us a few inklings of what's going on with this simple harmonic motion. There's another experiment I want to have a look at now. So let's go over and have a look at another experiment. Here I've got a different type of experiment, and here we've got our different length strings. The same mass, different length strings. Let's see what happens when we give these the same pull. Basically, you can see here very simply that they've all got different periods. The length of the string changes the period. They should all be nice patterns. Unfortunately, these two pairs are very, very similar. But we get interesting patterns start to appear as this goes on. And as time goes by, firstly the amplitude will die away, but what we should see is in fact they start to make repeating patterns. So the size, the length of the string is going to change the period. The ones that are this end, the longest string, have a very different period than the ones with the shortest strings. The shorter strings move faster than the larger ones. We're getting back to a shape. What I'm losing, unfortunately, is an awful lot of amplitude as it does so. I also don't want to give it too big a swing, because too big a swing affects the simple harmonic motion. But we can see as time goes on, then we get different patterns starting to emerge. And although you can see some this way, what I'm going to do is I'm just going to slow it down and stop it. You can see there we've got a different pattern. What I'm going to do is I'm going to adjust this so that you're going to look end on to the system, and what Paul's going to do is make sure the camera's lined up. I'm just going to line the camera up a bit. Oh, right, you moved the camera. About there. I've got a bit of blue tack trying to hold this down, trying to keep it a little bit more rigid. Let's look at it this way. And what we can start to see is perhaps different patterns emerging when we look at it this way. I'm hoping in a moment we're going to get a nice pattern where we get half the balls on one side and half on the other. Like that. So we can see how the length of this changes. And quite mesmerising those are. You can watch this normally for quite a long time. So there's our little introduction to simple harmonic motion. We've looked at a few features of simple harmonic motion and got some ideas about what it is and what it's doing. What we need to do now is start to investigate this in more detail and start looking at some formula to try and do this. And next time on A-level physics, topic by topic, we will do just that. So until next time, stay safe. And if you liked it, you can always subscribe. That way you'll make sure you get the next part. Thanks for watching. Bye bye.